Combining functions, for the sake of time, I think I want to skip this very first example. Could probably find, I've done it many times, could probably find a good video of it that I could send you a link to. But we'll give the definition, and then we'll look at the typical types of problems that you would expect either in ALEKS or on the test. Example 1 I don't think is going to be one of them. Operations on functions. Several different ways. We want to take functions and come up with either new functions or new expressions based on those original functions. First four correspond to the four arithmetic operations. Addition, subtraction, multiplication, and division. Where we know we can do that with real numbers, we want to see what it means to do that with functions. Actually take a function and add it to another function and define a new function based on that operation. We call it the sum of two functions, the difference of two functions, the product of two functions, and the quotient of two functions. And the definitions, hopefully, are kind of what you would expect. F plus g is the sum of the functions f and g. If we want to evaluate the function f plus g at a number, we evaluate f at that number, we evaluate g at that number, and we add those two function values together. So, for example, if f of x equals 2x plus 3, and g of x equals x squared minus 5, and we wanted to find f of 4, well, that would be easy enough. If we want to find g of 4, that hopefully would be easy enough. The point here is, what if we wanted to find f plus g of 4? Well, let's see. F of 4 is going to be 2 times 4 plus 3. That's 8 plus 3. That's 11. And g of 4 is 4 squared minus 5. No way. Did not want that to happen. How do I fix this? Hate when that happens. How about 2x squared minus 5? There we go. So it's going to be 4 squared is 16. 16 times 2 is 32, and 32 minus 5 is 27. There we go. So we find f of 4, we find g of 4. If we want to find f plus g of 4, the definition says it's whatever f of 4 plus g of 4 is. So we evaluate the function separately, we get an answer, and we add those answers together. 11 plus, we get answers for each one, then we add them together. 11 plus 27 is 38. So f plus g of 4 equals 38. Now, another approach we could take to this is actually come up with an expression for f plus g of 4, or for f plus g of x, and then evaluate that at 4. So you could say f plus g of x is f of x plus g of x, and so f plus g of x is 2x plus 3 plus 2x squared minus 5, and come up with the expression combine like terms. There are a couple of like terms I think we can combine, the constant terms. 2x squared plus 2x minus 2. And then if we want to find f plus g of 4, we just say 2 times 4 squared plus 2 times 4 minus 2, and we hope against hope that we get 38 here. It's going to be 2 times 16, that's 32. 2 times 4 is 8. Subtract the 2, that's 40 minus 2, which is 38. So f plus g of a number, you can find f of that number, you can find g of that number, you can add them together, and that gives you f plus g of that number. Or, since the function is defined in terms of x, we could find f plus g of x by calculating f of x, writing expressions for f of x and g of x, and then adding those expressions together to come up with an expression for f plus g of x, and then substituting 4 into that expression. Either way, Get the same answer there. Similarly, f minus g is defined by finding f of x and g of x and then subtracting. Fg is defined by finding f of x and g of x and then multiplying. And f over g is defined as taking f of x and g of x, and so long as g of x is not 0, we can divide, and then we have our function. To settle the question of domain, Alex may ask you the domain of a sum, difference, product, or quotient. In this case, they're both polynomials. They both have all real numbers in their domains. So the only concern might be what makes g of x equal to 0. And this is particularly awkward. I think it's some irrational number that makes g of x equal to 0. That would be the only restriction on the domain. We'll look at a problem later and see if we can find any restrictions on the domains of f plus g, f minus g, fg, and f over g. It may be sooner than later. Let's look at example 2. Example 2. Okay. Should be nice enough. Don't let me forget the e part and the f part. A couple of nice linear functions. We can do these problems a couple of ways. Let's go ahead and find f plus g of x. That's going to be f of x plus g of x. That's going to be 3x minus 1 plus 4x plus 2, which I'm pretty sure is 7x plus 1. Just add the algebraic expressions together. Get an algebraic expression and use that to define f plus g of x. So for the a part at least, let's look at two different ways of finding f plus g of 1. One way is to find f of, well, negative 1, sorry. F of negative 1 plus g of negative 1. Can we stare this down and figure out what f of negative 1 is? 3 times negative 1, negative 3, minus 1, negative 4. Does that look right? How about g of negative 1? 4 times negative 1, negative 4 plus 2, negative 2. So it's negative 6. Evaluate f of the number, evaluate g of the number, add. If I added correctly, if I evaluated correctly, if I added correctly, it's negative 6. Alternatively, if we believe that f plus g of x equals 7x plus 1, then f plus g of negative 1 should be 7 times negative 1 plus 1. That's negative 7 plus 1. That's also negative 6. So evaluate the functions and add them, or evaluate the or calculate the sum function by adding the expressions and then evaluate that. For the b part, c part, and d part, I think all I want to do is just evaluate the individual functions. This is going to be f of 0 minus g of 0. Please do not think of this as applying the distributive property. This is not the distributive property here. We're not multiplying f by anything. We're just applying the definition of the difference function. F of the number minus g of the number. F of the number, f of 0 is negative 1. G of 0 is positive 2. And negative 1 minus 2 is negative 3. It didn't ask me for f minus g of x, so I didn't volunteer that information. F times g, evaluate that at negative 4. Officially, that's f of negative 4 times g of negative 4. Probably should go ahead and show my work on this one. 3 times negative 4 minus 1. I'm going to multiply that by 4 times negative 4 plus 2. I think we can call this negative 13. We can call this negative 14. Do I know what negative 13 times negative 14 is? Well, positive 13 times positive 14 is 182. So I'm thinking negative 13 times negative 14 is the same thing. 182. Fg of that number. And f over g of 2. we find f of 2, we find g of 2, and so long as g of 2 is not 0, we divide. So f of 2 is 3 times 2 is 6, 6 minus 1 is 5. G of 2, 4 times 2 is 8, 8 plus 2 is 10. So I'm thinking it's 5 over 10. Reduce if you can. So 1/2. Does it seem too simple? I think it's supposed to seem too simple at this point. It actually doesn't get a whole lot more complicated than this. It's just a matter of learning the definition and applying the definition of the sum difference product or quotient of two functions. This is how to evaluate them. The E part. F plus g of x. I think I did that, didn't I? I sure did. There it is. F plus g of x. So that's done, and in fact, actually, I did more than that. F plus g of x is 7x plus 1. I just applied it to -1. And, wow, okay. I did the f part also. F plus g of -1. When x equals negative, f plus g of x when x equals -1, that's equal to -6. So evidently it's important because I did it before I even realized that's what I was needing to do. Goodness. Let's see if I've got an example here that specifically asks for domains and ranges. Let's look at example 4. Let f of x equal x squared minus 6x plus 8. Let g of x equal x minus 2. The domain of the sum, difference, and product are always equal to the same thing as each other. That's why it all appears in the same thing, f plus g, f minus g, and fg. Because in order to evaluate f plus g at x, you have to be able to evaluate f at x and you have to evaluate g at x. So x has to be in the domain of both of those. On the other hand, if x is in the domain of both of those functions, you can evaluate f at x, you can evaluate g at x, and you can add them. So the domain of all three of these functions, f plus g, f minus g, and fg, is exactly what the domains of f and g have in common. So we find one of them, we got all three of them. The domain of f over g can't be any more than that, but it could be less. Basically, we start with the common domain of f plus g, f minus g, and fg, and kick out any number that makes g of x equal to 0. Because we can't divide by 0, and if we're trying to divide by g of x, well, x is no good for us. So, and g of x is 0, x would be no good. So let's look at the domain of f. These are polynomials, x squared minus 6x plus 8. We can pick an x, any real number x, no problem squaring it, no problem multiplying by 6, no problem subtracting, no problem adding. Same with the x minus 2, it's all real numbers. All real numbers in the domain of this function. No bad values of x at all. We get bad values of x sometimes if it's an x that's going to cause us to divide by 0. None of that going on. Sometimes if it's going to cause us to take the square root of a negative number. None of that going on. All real numbers are good for this function. All real numbers are good for the function g as well. Pick a real number, any real number. Subtract 2. Is that going to be on the real number line? Definitely. Just 2 units to the left of wherever x was. So all real numbers in the domain there. So, what does for the C part here, what does the set of all real numbers have in common with the set of all real numbers? I'm thinking the set of all real numbers. You take all real numbers and form the union with itself, you get the set of all real numbers. So no excitement yet to this problem. The only real challenge here is the D part, where we take the set of all real numbers and ask, is there one or more of them that makes g of x equal to 0? And there's one. What number can you substitute for x, subtract 2, and get 0? 2. So 2 is bad. If we were to try to find f over g of 2, that would be f of 2 divided by g of 2. Well, f of 2 actually I think is, it might be 0. 2 squared is 4. 6 times 2 is 12. 4 minus 12 is negative 8, I guess. And negative 8 plus 8 is 0. I think it actually is 0. But the fact that the denominator is 0 makes this an undefined expression. So it's still undefined. And it's not because the numerator was 0. It's because the denominator was 0. Excuse me. So it's undefined. So everything to the left of 2 is good. And everything to the right of 2 is good. But 2 itself is not good because it makes the denominator 0. And we can't have that. So we have to exclude the number that makes the denominator 0. Now, just the domains. It did not ask us to find f plus g, f minus g, f g. Maybe it'll ask us that as I scroll down. Sadly, it does. Yeah. So we found their domains. Now we just need expressions. Expressions for them. So let's paste that in there. Whoa. Not what I expected to have copied there. And just a friendly reminder, what were those functions? There. Come on. Get in a hurry sometimes. That's where I want to paste it. So those are the functions. We've got their domains. All real numbers in the domains of sum, difference, and product. Everything but the number 2 in the domain of the quotient. Let's write these expressions and simplify as much as possible. This is going to equal f of x plus g of x. So this is going to be x squared minus 6x plus 8 plus x minus 2. In the case of the sum, the parentheses really aren't all that crucial. Basically, they vanish and we combine like terms and get x squared minus 5x plus 6. If you want to factor that, you're welcome to, but it's not necessary. There's nothing about this that says you should try to factor that, so I would just leave it in unfactored form. That way you don't risk making a mistake with an unnecessary step. F minus g of x, that's going to be f of x minus g of x. So you take the x squared minus 6x plus 8 and subtract x minus 2. The parentheses are kind of a big deal for the x minus 2 at least, because if we're subtracting x minus 2, that's equivalent to adding negative x plus 2. So distribute the negative sign across the parentheses. So we get x squared minus 6x plus 8 minus x plus 2, and combine like terms. X squared minus 7x plus 10. That 2 can be factored, but I would caution you against it. It's just not necessary, so I'm thinking leave it like that. Fg of x, oh, this is one that's kind of a pain. Practice multiplying polynomials. F of x times g of x, so it's going to be x squared minus 6x plus 8 times x minus 2. I don't know if I can give you full credit for leaving it like that. I'm not sure Alex would either. You could try it and see if Alex asks you something like that. It may not. I think I would want you to simplify. I simplified this expression, I simplified this expression. I'm thinking simplify that expression too. We can do this. We can multiply a trinomial by binomial. There are a couple different ways to do it. I'm going to suggest multiplying x squared by the x minus 2, multiplying negative 6x by the x minus 2, and multiplying the 8 by the x minus 2. Basically, if we've got two polynomials multiplied together, every term in one of them has to be multiplied by every term in the other. So we're basically applying the distributive property here. Keep applying the distributive property. X cubed minus 2x squared minus 6x squared plus 12x plus 8x minus 16. And then it's x cubed minus 8x squared plus 20x minus 16. Now, should we try to factor that? No, because we could get something similar to what we started with. So leave that alone there. And then f over g. F over g is f of x over g of x. It's x squared minus 6x plus 8 over x minus 2. Now here's a case where it might be to our advantage to factor the numerator, because the idea is simplify. We want to write this in as simple a form as possible. I feel like I need more space for it. And there's no place. Maybe if I scoot this over a little bit. Perhaps if we did factor, it would be x minus 2 times x minus 4 over x minus 2. Now notice, we're going to scratch out the x minus 2's because we're going to reduce this rational expression to lowest terms, and we're going to say this is x minus 4. That does not change the fact that 2 is not in the domain of the quotient function. Now if I just defined a function from scratch and said it's h of x equals x minus 4, that's a polynomial that would have all real numbers in its domain. But there's more to it than that. This function is defined as being the quotient of these other two functions, and if we cannot substitute 2 for x here and evaluate this expression, it really doesn't matter. 2 minus 4 is not going to be a meaningful value for us. So it doesn't change the domain. The domain is still everything but 2. It just gives us an easier way of evaluating this. If I want to evaluate f of 5, it's way easier to say 5 minus 4 than it is to say 5 squared minus 6 times 5 plus 8, enter, divided by whatever 5 minus 2 is. Way easier to say 5 minus 4. So we like the simpler expression. We just know that doesn't have any impact on the domain of the expression. So which one? Let's talk difference quotient. Let's talk difference quotient. Probably do the second one in a matter of 5 minutes. Difference quotient is defined as f of x plus h. Go back to dark blue here. F of x plus h minus f of x all over h. Basically, it's the slope of the line connecting 2 points on the graph of a function. If we have the graph of a function, and there's x, and there's x plus h, and there's the point x f of x, and there's the point x plus h f of x plus h, and we connect the dots with a straight line, like that. The slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, gives us f of x plus h minus f of x over x plus h minus x, which is f of x plus h minus f of x divided by h. Basically, it tells us the average rate of change of the function on this interval from x to x plus h. And it turns out to be a really important ratio in calculating average rate of change and in leading to the notion of instantaneous rate of change, which is a very important concept in calculus. So I want to see if I can look at the b parts. The computation is a little bit on the tedious side, but with 4 minutes and change, might be able to get through this. So the b part, I want to do this piecemeal. First, I want to find f of x plus h. F of x plus h. So it's a matter of substituting x plus h for x wherever we see an x. So 3 times x plus h quantity squared minus 2 times x plus h minus 4. And a couple steps to simplify this. We need to square the x plus h. We get x squared plus 2xh plus h squared minus 2x minus 2h minus 4. And then distribute the, everyone feel good about where the 2xh came from? 2xh. We're squaring the x plus h. That's, you can FOIL it with itself. You get an x squared, you get an xh, you get another xh for the o and the I. That's 2xh. And then simplify. We get 3x squared plus 6xh plus 3h squared minus 2x minus 2h minus 4. That's the biggest part of it. That's not the whole thing, but that's the biggest part of it. We can take this, that's just this much of it right there. We're going to take that and substitute it into that great big difference quotient. So f of x plus h minus f of x all over h. So this, all of this, is going to go right here. And all of, where is it? This is going to go right here. It's f of x plus h. We have an expression for that. 6 terms, but it's an expression for that nonetheless. Then it's f of x. That's 3 terms. 9 terms up there. And nothing but an h in the denominator. Good news is, when we simplify the numerator, 6 out of 9 of those terms up there are going to cancel. So we're going to have 3x squared plus 6xh plus 3h squared minus 2x minus 2h minus 4 minus the quantity 3x squared minus 2x minus 4. And we begin to simplify. Clear the parentheses. A lot of copying and pasting at this step. 3x squared plus 6xh plus 3h squared minus 2x minus 2h minus 4 minus 3x squared plus 2x plus 4 all over h. Now at this point in the process, every term that does not have an h in it in the numerator must cancel. Otherwise, something has gone very wrong. 3x squared and minus 3x squared cancel. And then minus 2x and plus 2x cancel, and then minus 4 and plus 4 cancel. 6 out of those 9 terms cancel, and it leaves us with 6xh plus 3h squared minus 2h all over h. Now the most practical use of a difference quotient is maybe not so much the average rate of change, but the instantaneous rate of change. So what we want to do is get to the point where we can substitute 0 for h and actually calculate the instantaneous rate of change. Well, we can't do that until we get the h out of the denominator. So the problem's not done until we get the h out of the denominator, but no trouble there. We can factor an h out of the numerator because every term has a factor of h in it. And once that's done, we can divide both the numerator and denominator by h. And it leaves us with 6x plus 3h minus 2. Maybe not a terribly satisfying final answer. But basically it's telling us that if we pick 2 points on the graph, one of which has an x-coordinate of x, and another one has an x-coordinate h units more than that, and we substitute that x and that h into this expression, it will tell us the slope of the line connecting those 2 points on the graph. and it'll give us the idea of how rapidly the function's changing on that particular interval. When we go back to section 2.8, we had done most of that. I want to pick up with the topic of composition of functions. We're still combining functions in this section. We combined them last time by adding, subtracting, multiplying, dividing, just based on the arithmetic operations where we evaluate the function f and g at the same number x and either add those two function values, subtract, multiply, or divide, as long as we're not dividing both sides. We're dividing by 0. Well, in composition of functions, you may have seen this sort of thing before. We're evaluating the function f and we're evaluating the function g, but not necessarily at the same number. I really like to think of the idea of composition of functions as the work of functions doing work on an assembly line. It makes it clear in my head, and hopefully it helps a few other folks. Let's look at the notation. This notation, f and then a little circle and then a g. We read that f composed with g. And that's the name of the function right there, f composed with g, as we would write it. If we want to take that combined function, that composite function, and evaluate it at x, the rules for doing so go like this. Begin on the right with that function g, because that's the one written on the right, and evaluate g at x. And get an answer. X has to be in the domain of g in order to be able to do this. So get an answer. Now that answer has to be in the domain of f, because you're going to evaluate the function f at whatever answer you get. So typically, when you're finding f composed with g, f and g don't end up getting evaluated at exactly the same number. I think of a number coming down an assembly line and then getting to the g station, and then g does what it does. It produces g of that number, g of x, and then the number g of x goes on down the line to the next station, the f station. And then f does what it does to g of x, and then that's the final product, f of g of x. So that's the way I think of it. And as we look at examples of this, I will do the hand motions, various things to simulate numbers coming down an assembly line. That's just the way I see it. Let's look at example 7, get some practice with this. We've got a couple of nice functions, a linear function, a quadratic function, and we want to find f composed with g of -3. So f composed with g, if we want to use the definition here, and that is the best way to do it, this literally means f of g of -3. We're trying to find the result of evaluating g at -3, getting an answer, and evaluating f at that answer. So g of -3, g, we will look at the g function. First, that's the function that first squares a number and then subtracts 2 from it. So g is going to take that -3 and, whoa, don't need to, well, yes, I do. G is going to take that -3, square it, and then subtract 2. That's what g does all day long. When it does that to -3, -3 squared is 9, and 9 minus 2 is 7. -3 has come down the line, it's reached the g station, g takes the -3. Input -3, it outputs a 7, and then 7 keeps on going down the line, it gets to the f station, and then f does what it does. Function f in this case is the function that takes a number and adds 1 to it. So it takes the 7, and it adds 1 to it, and it gets 8. So if the two processes are squares and then subtracts 2, and then adds 1, and it begins with the original input is -3. If you take -3 and square it, and then subtract 2, and then add 1, you end up with 8. So that's the idea of this composite. Now, if we reverse those, we're going to start with -3. -3 is going to come down the line, but we're going to reverse the order of the stations. The first station is going to be the station that first adds 1. And then after adding 1, it's going to keep on going down the line, and then it's going to get to the station that squares and then subtracts 2. So sometimes when you do this and you reverse the functions, you get the same answer. Most of the time, though, you get a different answer. Let's see what it is in this case. It's going to be g of f of -3. So first thing we're doing is we're taking that -3 and we are adding 1. So we add 1 to the negative 3 and get negative 2. Negative 2 continues on down the line, gets to the G station now. G does what it does. It squares the negative 2, and then it subtracts 2. And 4 minus 2 is 2. So a different final answer. So evidently, for these two particular functions, the order in which the composition is done turns out to be important. It makes a difference. Change the order, and it has the distinct possibility, certainly in the case of negative 3, of changing the final result. Now, there are certainly situations in which we'd like to express the final result in terms of the original input. We will get to that. But first consider these two other possibilities. It's possible to have two copies of the same station. We've got something coming down the assembly line, and there's an F station that does whatever it does, and there's another F station that does exactly the same thing. I don't know, maybe it's putting on a coat of paint, and it's another one that puts on another coat of paint, exactly the same way. If our F station is simply it adds 1, then the next F station would add 1 more. And I'm thinking if you send 3 past 2 of those stations, it's going to output 4 to the first one. When the 4 goes in, it's going to output a 5. So it's going to be F of whatever 3 plus 1 is. 3 goes in, 4 comes out. 4 goes in, 5 comes out. So F composed with F of 3 outputs a 5. G composed with G of 0. This is G of 0. So G is still squaring and subtracting 2, squaring and subtracting 2. So it takes the 0, it squares it, it subtracts 2, and gets negative 2. Then it takes the negative 2 and squares that and subtracts 2. And it gets, what, positive 2? Just got to make this observation. It is possible to have as many functions on the assembly line as we want. If we want to say F composed with G composed with H, we're more than welcome to do that. It just means evaluate H first, get an answer, evaluate G at that answer, get another answer, and evaluate F at that answer, working our way from right to left as the functions are indicated there in the definition. We could just as well find G composed with G composed with G composed with G of 0. And it's maybe interesting to see what's the long-term result of carrying out that process as often as we need to. Now, as far as if we just want to go F composed with F composed with F composed with F, it's just going to add 1 each time, and the outputs are going to be 4, 5, 6, 7, 8, 9, and that's maybe not going to be all that interesting. This particular function G, I just happen to notice this, put in 0, you get negative 2. And if you put in negative 2, you get positive 2. What if you put in positive 2? Square it and subtract 2. You get the positive 2 right back. So if you were to keep doing that, put in positive 2, get out positive 2, and run it through again and run it through again, it doesn't change. So if we were to calculate G composed with G composed with G composed with G as many times as you want, well, the first couple times, composed with 0, I suppose. You got to get to the 2 before it starts doing this. But if you start at 0, you're eventually going to get 2, and it's just going to keep being 2. Once you do this at least 2 times to 0. So just an observation there. Sometimes it just keeps going off to infinity. Sometimes maybe jumping back and forth. In this case, it jumps around just a little bit, and when it gets to 2, it stays there. And it doesn't, evidently the function g doesn't have any effect on 2. Can perform that as often as you want to the number 2, and it just stays right there. Domain. Alex may ask you for the domain of the composition of two functions. I think there's kind of a description here of how to calculate the domain, but in this original definition, all x in the domain of g of x such that g of x is in the domain of f of x. There's a picture that goes with this. I think I may skip the picture though. Basically, x is going to be in the domain of the composition if we think of it in terms of the assembly line. I don't know if I've thought of it like that before, but it has to be a situation where x can go in and the machine will accept it. And if it accepts it, it's got to convert it into something that the f machine will accept. If it's something like f of x equals 1 over x minus 3, g of x equals 1 over x minus 5, what's the one number that the g function will not accept? Will not accept 5. So 5 would be disallowed from the domain. Now, would the number 3 be okay for the composition, you think? You take 3 and you put it in the g function, and the g function's happy with the 3. And what does the g function do with the 3? What does it output? Like negative 1/2. 3 minus 5 is negative 2. 1 over negative 2 is, so it outputs a negative 1/2, and then it's a negative 1/2 that goes over to the f function. Is the f function going to be happy with the negative 1/2? Sure, yeah. F function will have a problem with the 3, but it's good with a negative 1/2. So 3 would be fine. That would be in the domain, whereas 5 would not be. Now, the one that's sometimes tricky to find is this. What number is g going to output that f is going to have a problem with? It's going to have a problem with 3. So here's the question. What number can we input to the g function so that we'll output a 3? Well, if we put in an 8, it'll output a 1/3. It's a little tricky. You might even have to write something down to get this. What can you input? What can you subtract 5 from and take the reciprocal of and get 3 as the answer? Probably some number pretty close to 5. A little more than 5. Maybe 5 1/3. Will that do it? Put a 5 1/3 there. I mean, I know way back in section 1.5 we solved equations like this. You multiply both sides by x minus 5, and then you get the x terms on one side, constant terms on the other, and solve it. We'd probably get it. But does this work? Let's see. Okay, so we come back here. Here's a 5 1/3. It's coming down the line. It gets to the g station, and g's cool with it. 5 1/3 minus 5 is 1/3, and 1 divided by 1/3 is 3. So out pops a 3, and then it goes on down the line, and f says, no way, not going to accept that 3, and it kicks it out. And so what we say is, because in order to satisfy the process, it's got to get through both of the functions. The 5 1/3 is bad, because when g accepts it, it outputs a number that f will not accept. So x is not allowed to be 5 because g will not accept it. But x is also not allowed to be 5 1/3 because although g will accept it, it outputs a number that f will not accept. So two numbers that fail to be in the domain of this function. I think all other real numbers are good, because g will accept everything other than a 5, and f will accept everything other than 3, and I think 5 1/3 is the only number that produces that 3 that f doesn't like. So these are the only two bad values of x. But you can see, looking at this denominator, looking at this denominator, 5 1/3 really doesn't show up anywhere. You have to go kind of looking around for that 5 1/3, thinking about it a little bit. So that's kind of how we look at the domain of the composition of two functions. that second bad value of x in a problem like this is sometimes a little tricky to find. So let's look at this next example. We've got a similar type of problem in example 8. If f of x equals 1 over x minus 5 and g of x equals 1 over x, find the composition and the domain of the composition. Well, let's do the very straightforward part first. Let's actually find f composed with g of x, which is f of g of x. It just requires substitution. So if we had a specific number to put into the g function, we'd put it in and see what g gives us, but we don't. All we can say it's whatever 1 over x is. That's what the function g does. It accepts a number x, and then it outputs the reciprocal of that number, 1 over x. F has to take that, and when it takes it, if it can take it, it will evaluate this rational function, 1 over x minus 5. And so we take that reciprocal of x from g, and then subtract 5, and then take the reciprocal of that. Now we want to simplify this as much as possible. It's a complex fraction as it is. We'd rather not leave our final answer as a complex fraction if we can avoid it. So my suggestion for simplifying this, it's crazy. There are basically two methods for simplifying complex fractions, but I tell my intermediate algebra students, you never know which one your college algebra instructor is going to use to simplify it. And if you're not familiar with method 2, then it might be confusing. Well, here's method 2. What is the value of x over x? It's 1. So long as x is not 0, we don't want x to be 0. It's 1. So what we want to do is multiply by 1. When you multiply by 1, you can change the way an expression looks without changing its value. That's what we want to do. 1 times x is x. Now, if we take that x down in the denominator and distribute it across the 1 over x minus 5, x times 1 over x gives us 1, and x times negative 5 gives us negative 5x. Not the only way to simplify that complex fraction. You could get a common denominator in the denominator and subtract, and then divide by the fraction that you get. But this is a little shorter, a little sweeter way of getting it done. So x over 1 minus 5x. Now, that's f composed with g of x. What that tells us is that if we input a number that's in the domain of the composition, and it goes through the function g and out of the function g and into the function f and out of the function f, it'll give us a way of calculating the final output without having to evaluate the two functions individually. So just as a measure of how it works, let's pick something that we believe probably is in the domain of f composed with g. Something nice. 1 is probably nice enough, I guess. If we evaluate f composed with g at 1, if we send it into the g function, g says 1 divided by 1, and it outputs a 1. And then we send that 1 into the f function, and f subtracts 5 from the 1, gets negative 4 down the denominator, divides 1 by negative 4, and outputs negative 1/4. So we believe this is negative 1/4 just by evaluating the two functions individually. If we substitute 1 for x in the two places where we see an x in this rule we just came up with to define the composition, we get 1 over negative 4, which sure enough is negative 1/4. So that's what that expression does to us. It tells us, okay, you're going to input an x, it's going to go through g, it's going to go through f, it's going to come out the other side. What's it going to be? It's going to be x over the quantity 1 minus 5x. What's the domain of the composition? Now there are two places to look, and this can maybe help us avoid having to carry out some of the clever thinking that we did on the other side. We can look at this and kind of find bad values of x in various places. First thing that's going to happen is that the function g has to accept the x. But there's one particular value of x that g is going to have a real problem with, and what's that going to be? 0. 0 is bad. Can't divide 1 by 0. So 0 is bad. 0 is not in the domain of this function. Now, the other one, we could ask, well, what number is going to come out of the g function that f is going to have a problem with? Well, what number is f going to have a problem with? If you present f with x equals 5, that would be a problem. But 5 is in the domain of the function f composed with g, because if g gets that 5, it's going to turn it into 1/5. And when g turns into 1/5, f is going to be happy with it. It's going to be cool. But what number is g going to get that f is not going to like? That's going to turn it into a number that f is not going to like? Yeah, I think that's the way to say it. What number is g going to turn into a 5? How about that? It's going to come into g, and g is going to say, okay, I'm going to do what I do and output 5. What's it going to be? Is it going to be 1/5? You input 1/5, and g is the reciprocal function. G takes the reciprocal of everything you give it. So you input 1/5, and g outputs 5, and that 5 comes on down the line, and f says, no way, not taking it. So 1/5 is not in the domain of this composition. Now, notice in our final answer, 1/5 is the bad value of x, right? If you say 1 minus 5x equals 0, subtract 1 from both sides, negative 5x equals negative 1, divide both sides by negative 5x equals 1/5. Okay, by looking at that denominator, you can tell that 1/5 is bad. By looking at this denominator, you can tell that 0 is bad. So without having to perform the mental gymnastics that we seem to have been having to do in these last couple of examples, you can get at the bad values of x. Just go looking for denominators all throughout the problem, and every time you see a denominator, realize that any value of x that causes that denominator to be 0 is going to be a problem. So the domain of f composed with g is everything between negative infinity and 0, everything between 0 and 1/5, and everything between 1/5 and positive infinity. 0 is bad because g will not accept it, and 1/5 is bad because g turns that into a 5, which f will not accept. So that's the domain. Let's see, decomposition. Let's look at example 9. Example 9, I think Alex does give you one problem like this. Express the given function h as the composition of two functions f and g such that h of x equals f composed with g of x. Well, let's suppose h is a single station on an assembly line, and it's been doing a good job, but it's getting tired. And it feels like it's overworked, and it's beginning to moan and groan a little bit. And so management looks at the situation and decides, well, probably get more efficiency out of that station if we can divide the labor between two other stations that might individually stay strong and not need as much maintenance throughout the day. So what we're going to do is try to accomplish the same thing that the function h does, but share the load between two separate functions. So let's look and see what h does. See if we can figure a way to separate that into two different operations, and then assign those operations, one of them, to each of two different functions. So if we're evaluating the function h, say if I want to find h of 10, for example, maybe punch 10 into the calculator, and then what's the first thing I'm going to do with that 10? Subtract 1 from it. Okay, so first thing h does is it subtracts 1. That's what it does. Okay, so all day long, whenever something's presented to h, it subtracts 1. But before sending it on its way, after it subtracts 1, it's got to do what? It's got to take the square root, right? Yeah, subtracts 1, takes the square root, sends it on its way. Subtracts 1, takes the square root, sends it on its way. All day long. Well, that's too much. That's too much. So what we want to do is take these two operations and distribute them between two separate stations. I want to make sure we get them in the right order, because subtracting 1 and taking the square root, is that guaranteed to produce the same final answer as first taking the square root and then subtracting 1? Maybe that's obvious, maybe it's not. If we start with 10 and we subtract 1, we get 9. We take the square root, we get 3. So if 10 comes in, 3 goes out. But if we reverse those two, if we take the square root first, we get the square root of 10, and then we subtract 1 from that, we'd get the square root of 10 minus 1. 3 square root of 10 is 3 point something. 1 less than that is 2 point something. We're not going to get the 3 to come out of there. So got to get them in the right order. So I'm going to let G be the first one, because when you write the composition, the first function that gets evaluated is the one on the right. So the G function needs to be the function that subtracts 1, and the function that does nothing except subtract 1 can be defined by the algebraic expression x minus 1. So it comes down to the function G. G subtracts 1 from it, so a 10 comes in, a 9 goes out. And then the 9 is working its way down to the f function. And what's the f function need to do to that? It needs to take the square root of it, so square root of x. So 10 comes in, 9 goes out to the g function, 9 goes into the f function, 3 comes out. And so the two functions individually, their combined effort is doing the same work, hopefully more efficiently and with less moaning and groaning than the single function h. So if we check our work, final answer to this problem, scoot this over, scoot this up. Final answer to this problem is this. Evidently, and be careful, because I think the boxes Alex gives you, I think it puts the f of x function on top and the g of x function on the bottom. So if I'm working the problem, I'm probably going to want to fill in the g of x on the bottom first, and then the f of x function up above that. So you might want to keep that in mind when you're entering your answer there. It might be helpful, yes.
Does it really matter what line you put for each function? Do you have to do g first, or could you just recall x minus 1 f of x instead? And then the g of x equals square root of x?
If you switch them, if you say f of x equals x minus 1 and g of x equals the square root of x, we'll just do the composition. If we want to compose f with g, we would get f of x minus 1, which is the square root of x minus 1. And that's h of x. If we reverse it, or I guess I've relabeled them, since I've relabeled them, if we try f composed with g of x in this case, it would be f of g of x, which is f of the square root of x, which is the square root of x minus 1. F takes the square root. So just so I'm understanding your question, I think the answer to your question boils down to this one. Is this expression equivalent to that one? Does it matter whether the minus 1 is underneath the radical sign or not? And in some cases, for some functions with special relationships to each other, it doesn't matter. You can reverse the two functions and it'll accomplish exactly the same task. You can say, suppose you got a function that adds 5 and then a function that subtracts 10. Okay? And so we go in, we add 5 and then subtract 10, add 5, subtract 10. Is that any different from first subtracting 10 and then adding 5? I think the net result is, I think ultimately, what? I don't know if I said that right. Maybe I didn't say it right. Let me write it down. F of x equals x. Let's say adding 10 and subtracting 5. Add 10 and subtract 5. Is that any different from subtracting 5 first and then adding 10? I think the net result of both, whether it's, and I should give them different names, gee whiz. F composed with g of x, I think is going to be x plus 5, and I think g composed with f of x is also going to be x plus 5. Y'all should check that and see if that's what you get. But I think the order doesn't matter in that case. But with these, I think it does. I think it does matter. So just do the composition both ways and see if when you do the composition you actually do get that expression or something equivalent to that expression.
But you're always evaluating g of x first in that case.
Well, whichever
is composed of g of x.
Right, whichever one's on the right.
Right.
Now, if you wanted to break it down and call the first function f and the second function g, that's fine. Just call it g composed with f. If you say g composed with f, then you can do the f function first and then the g function second. Just whatever function's on the right when you write the composition, that's the one that goes first, and you work your way from right to left from there. The B part. What's that going to look like? 3 things going on here. Oops, sorry about that, y'all. 3 things going on here. The B part, you've got x coming in. It gets multiplied by 3. It has 2 added to it, and then its absolute value is being taken. So multiply by 3, add 2, take absolute value. Now there's considerable flexibility here, and I'm hoping Alex is aware that there, in fact, I'm not hoping, I'm distrusting that Alex is aware of this, because they stated in the problem that there's several different ways to do what it is they ask you to do, and I'm just hoping when they grade it and evaluate your answer, they say, yeah, that's right, if you choose any one of several correct ways. So we got a function, h, that does 3 things all day long. Multiplying by 3, adding 2, taking the absolute value, sending on down the line. Multiplying by 3, adding 2, taking the absolute value, sending on down the line. And we want to take those 3 operations, basically, and divide that between 2 separate functions. In this order, what's one way to do it?
G of x equals 3x plus 2.
That would be one way to do it. Letting g do the first 2 out of 3 operations and send it on down the line so that f, all it has to do is what? F's got a cush job, because maybe half the time it doesn't have to do anything at all, right? If it comes down as positive, F says, cool, I'll just what? Keep resting here. So anyway, f, all it has to do is take the absolute value. So that's one way to do it, and you can show that f composed with g of x is h. What is another way to do it?
G of x is equal to 3x, and then f of x is equal to x plus 2. Yes. Let g just do the first thing. Just to multiply by 3, if it comes down the line to f, and that 2 hasn't been added yet, then f has to do that. F has to add the 2, and then take the absolute value. Just like that. Add the 2, take the absolute value, and then you should check that the composition of these 2 functions, f composed with g, does in fact equal that original h up there. Now what Alex will say, neither function can be the identity function. Y'all remember we spoke just briefly about the identity function when we were talking library of functions right before we started shifting and stretching all over the place?
Identity function. What is the identity function? F of x equals what? Anybody remember that? Identity function. I call it the do nothing function. It takes a number and does absolutely nothing with it. Input an x and it outputs an x. The identity function is what we call that. And Alex says, it's good that we know this, because when Alex says don't use the identity function, it's good to know what function you're not supposed to be using. Don't use this function as one of the possibilities, because, I mean, this is a function that's even lazier than the absolute value function, right? Because we want to give h a break, but if our g function, for example, does nothing at all, then our f function, once it gets there, has to do everything. It has to do the same thing that the original function h did. So you could do this technically by letting g of x be the do-nothing function and by letting f of x be the everything function. And if you compose any function with a do-nothing function, you get that function right back. So it's kind of a trivial way to do it. Also, you can imagine, you could let g function do everything, just over-enthusiastic. Not only does g multiply by 3 and add 2, but it takes the absolute value while it's at it, and then once it gets to f says, well, it's positive, heck, send it on down the line. And f does nothing at all. So Alex says, don't do this. Don't do this. Now, the reason for this, there's a key reason in calculus. If you want to find the derivative, whatever that is, of a function, then using the chain rule, whatever that is, being able to look at a function like this and mentally decompose it into two functions, g and f, whose composition is equal to this, is a very valuable skill, highly valued skill, and it makes the chain rule a lot easier to understand. If calculus or business calculus is not in your future, you don't have to worry about that, obviously, but it is an important deal. And college algebra is a place to talk about it, so that when students get to calculus, we can say, oh, remember back in college algebra when? All right. Enough said, maybe too much.